Είναι μεγάλη χαρά μου σήμερα να φιλοξενούμε στο πρώην της Θεσσαλονίκης νυν Διεθνές Πανεπιστήμιο μια εκλεκτή συνάδελφο, την κυρία Πετροπούλου Αθηνά και εξαιρετική επιστήμονα. Θα πω 5 λογάκια για την κυρία Πετροπούλου, η οποία μας έρχεται από την Αμερική. Βασικά την Καλαμάτα, δεν ξέρω. Μιλάει άψογα ελληνικά, οπότε μην έχετε πρόβλημα να ρωτήσετε οτιδήποτε. Είναι distinguished professor στο Electrical και Computer Engineering Department του Rutgers, του Πανεπιστημίου Rutgers, στο New Jersey των Ηνωμένων Πολιτειών, με το οποίο πανεπιστήμιο και συγκεκριμένα με το εργαστήριο της κυρίας Πετροπούλου έχουμε συνεργασία μέσω του Εράσμους. Είναι αυτό που σας έλεγα στο μάθημα, ότι ένας φοιτητής δικός μας μπορεί να κάνει μια τρίμηνη Εράσμους παραμονή στην Αμερική για να εκπληρώσει μέρος της διπλωματικής του εργασίας. Έχει υπάρξει visiting scholar στο Supélec Université Paris, SUD, στο Πανεπιστήμιο Princeton και στο University of Southern California. Ασχολείται με Statistical Signal Processing, Communications, Networking, Signal Processing and Networking, Physical Layer Security, Radar Signal Processing. Έχει πάρει μια σειρά από ερευνητικά έργα από το National Science Foundation, το Office of Naval Research, το US Army, το National Institute of Health, το Whitaker Foundation, τη Lockheed Martin. Είναι fellow της IEEE και της AAS, η οποία είναι η αμερικάνικη εταιρεία Aerospace. Το AAS.
No, American Society for the Advancement of Science.
Advancement of Science, συγγνώμη. Έχει πάρει το 1995 το Presidential Faculty Fellow Award, το οποίο το προσφέρει το NSF και ο Λευκός Οίκος. Έχει υπάρξει editor-in-chief σε διάφορα περιοδικά της IEEE, στο Transactions of Signal Processing, στο Signal Processing, έχει υπάρξει Signal Processing Society Vice President, conferences, member at large στο Signal Processing Board of Governors, σε πολλά συνέδρια. Πολύ πρόσφατα οργάνωσε το Signal Processing Advances in Wireless Communications στην Καλαμάτα. Πέρσι, σωστά. Και υπήρξε για τις τελευταίες 2 χρονιές, 17-18, Distinguished Lecturer της IEEE. Βασικά αυτό σημαίνει ότι επισκεπτόταν διάφορα μέρη, πανεπιστήμια και χώρες στον κόσμο και έδινε ομιλίες σχετικές με την έρευνα. Οπότε εγώ θα χαρώ πολύ να δώσω το λόγο στην κυρία Πετροπούλου να ακούσουμε τη σημερινή ομιλία. Ευχαριστούμε πολύ.
Ευχαριστώ πολύ για την εισαγωγή. Ο κ. Διαμαντάρας είχε έρθει στο Rutgers, στο πανεπιστήμιό μου, πριν μερικούς μήνες και συνεργαστήκαμε. Αυτό με κάλεσε να έρθω εδώ σήμερα. Μιλάω ελληνικά, αλλά δεν ξέρω την ορολογία. Οπότε θα σας παρουσιάσω το θέμα στα αγγλικά. Αλλά αν έχετε ερωτήσεις, ρωτήσετε στα ελληνικά. Πες με πώς το λέτε το Beamforming στα ελληνικά. Το λέμε.
Κάνετε Beamforming, έτσι.
Διαμόρφωση. Κατευθυντική διαμόρφωση.
Συν μία μονάδα.
Ωραία.
Σήμερα μιλάτε σήμερα μονάδες.
Είναι κανένας μέλος του IEEE?
Είναι students, δεν είστε students στο IEEE. Ποιοι είστε students, δεν είστε?
Δεν έχουμε
ένας μόνο.
αλλά πώς μπορούμε να έρθουμε σε επαφή με τη...
Ο Χατζημίσιος είναι υπεύθυνος για τους students στο IEEE, αλλά...
Έχουμε δικαίωμα με τα πτυχία εκεί.
Φυσικά, όλοι έχουν δικαίωμα.
Απλώς ήθελα να σας πω ότι είμαι υποψήφια για την προεδρία του IEEE Signal Processing Society και θα σταλούν ψήφοι σε όλα τα members. Οπότε θέλω να ζητήσω την ψήφο σας.
Όσοι είστε, αλλά δεν είδα και πολλούς.
Λοιπόν, το θέμα είναι πώς να βελτιστοποιήσεις το beamforming σε mobile networks.
Πάει έτσι, σβήστα όλα. Αφού έχει φως έξω. Τουλάχιστον έτσι. Ναι, καλό.
Η ιδέα είναι, φανταστείτε ότι είσαστε σε ένα στάδιο που έχει πάρα πολύ κόσμο και το τηλέφωνο σας δεν δουλεύει, γιατί όταν υπάρχει πολλής κόσμος, you exceed the capacity of the network. Οπότε σε αυτή την περίπτωση μπορεί κάποιος να στείλει ένα μήνος από δρόμους πάνω από το στάδιο και αυτά τα drones να βοηθήσουν σαν relays τα σήματα που θέλετε να στείλετε εσείς στο base station. Οπότε υπάρχουν πολλοί τρόποι να τα ταξινομήσεις αυτά τα drones πάνω από το στάδιο. Αυτό που συζητάω εδώ είναι ποιος είναι ο καλύτερος τρόπος να τα στήσεις αυτά τα drones. Βέβαια θα κινούνται, αλλά ποιος είναι ο καλύτερος τρόπος να κινούνται έτσι ώστε να επιτύχουν καλή κάλυψη του γηπέδου. Άλλες εφαρμογές είναι άμα υπάρχει κάποια καταστροφή, οπότε χαλάει το τηλεπικοινωνιακό δίκτυο, μπορεί να στείλεις πάλι ένα set από drones που να μπορέσει ο κόσμος να επικοινωνήσει με base stations. Είναι mathematical το formulation, αλλά θα προσπαθήσω να το εξηγήσω όσο πιο απλά γίνεται. Αυτή η δουλειά είναι του φοιτητή μου, Διονύση Καλογεριά, που τελείωσε το δακτορικό του, είναι μέρος του δακτορικού του και τώρα κάνει postdoc στο Princeton, στο Πανεπιστήμιο του Princeton και ήταν χρηματοδοτημένη από το National Science Foundation της Αμερικής. Οπότε, this is the relay beamforming problem. Έχουμε μια πηγή που θέλει να επικοινωνήσει με το destination, αλλά δεν έχει αρκετό power για να επικοινωνήσει με το destination. Σαν παράδειγμα, τα next generation networks θα χρησιμοποιήσουν millimeter waves. Millimeter waves experience a lot of attenuation, they cannot travel very far. So relays will be essential in order to use millimeter wave technology in next generation networks. So the relays will take the source signal and will do something to it and retransmit it. Now, what do? Imagine that the source sends sine waves, right? These guys will hear the source signal, and one way to help the communication is to retransmit what they hear after manipulating the signal a little bit. For example, if they hear sine waves, if they multiply the sine waves by some constants, they can make the sine waves add up in phase at the destination. So imagine if you have multiple waves, if you just send them all and they are added up, they can add up destructively. So one up, the other down will produce zero. But if you send them all so that their maxima are aligned, then they add up constructively and they end up in high power at the destination. So this is the goal of beamforming, to anticipate what the effect of this medium is and sort of delay its signal a little bit so that they add up constructively at the destination. So in that case you have maximum transfer of power at the destination. Another way to think of this is that these will act as antennas and they will transmit in a way that a beam is formed. Imagine it like a spotlight, and the spotlight will be shining at the destination. So over that beam, over the spotlight, you will have maximum transfer of power. So the problem in beamforming is how do you design the weights that the relays will use so that you have the best focused beam possible towards the destination. This is called the optimum weight design for the relays. So typically this problem had been studied for stationary nodes. The nodes do not move. And when they do not move, you can design the beams assuming that you know these channels. In this scenario, we studied the case where the nodes can move, they are mobile. So in addition to designing the weights, you can send them to the best possible positions. So you can model the effect of the propagation paths by these numbers. These are complex quantities. So the F are the channels from the source to the relays, and the G's are the channels from the relays to the destination. And these depend on the position. So the channel between this node and the destination is different than this node and the destination. And it turns out that some positions, PIs, result in very bad channels, very low quality channels. And you wouldn't want to transmit on a low quality channel. if you knew how the channel behaves, you'd want to send this guide to a location that experiences a good channel. So this is the problem that we're going to study, to design the locations of the relays and also the weights that we're going to assign to the channels. Now, how do you know the channels? The simplest way is to assume that there are channel maps. For example, you have deployed nodes in a network, like robots in a network, that have measured the channels at all possible positions. But over time, the channel changes with time. Of course, this is highly complex because the channel changes with time. You have a lot of points in a network. So although theoretically it's possible, in practice it's very difficult. However, there is some correlation between the channel here and the channel there. There is some correlation. And you know, when there is correlation, if I give you this, you can sort of predict the channel there. So this is the idea that we're going to use. We will use knowledge of the channels at locations we have visited and extrapolate that knowledge to estimate the channel at positions we have not visited. And based on our extrapolation from the channel, we'll try to send, if our belief for a channel is good, we'll send the relay to that position. So this is the idea. We're going to use statistics of the channels to guide the selection of position for the relays. So our work, the work that I'm going to describe appeared last December in the Ethical Transactions on Signal Processing. So here is the scenario. You're here in a stadium and you want to communicate with the base station, and we deploy these drones above the stadium that will keep moving, will keep changing positions. And what I'm going to present today will decide on the optimum positions for these relays at each time instant and assign the optimum weights to those relays so that the signal to the destination, the base station for example, is received in high power. Okay, so we consider a network with our mobile relays. We'll model the channels as random processes. And the channels are correlated in time and space. We'll assume that the channel is causal. In other words, you only know the channel to the positions you have visited. You don't know the channel everywhere else. So somehow we'll use the fact that the channels are correlated to extrapolate the channel in time and space in the future and in positions that we have not visited. We'll assume also that the relays can exchange small messages locally. So before I explain the method, let's discuss a model for the channel. So we'll assume flat fading channel model. In other words, the signal going through the flat fading channel is also changed by multiplication by a complex number, f. And the complex number is function of the position and time. And the channel has three multiplicative terms. The first one is the attenuation term, defined like this. So if PS is the location of the source, then the attenuation term is basically 1 over the Euclidean distance between the position P and the source position, raised to the power L over 2. So L is the path loss exponent. So the larger L, the faster the signal decays, the channel decays. So if you think that the signal is multiplied by the channel, the larger the L, the faster the signal decays. The red term is the shadowing term. So this represents the effect of large obstacles in the path of a signal. You have buildings, huge buildings. Everything that is much larger than the signal wavelength experiences shadowing. And the last term, is there a question?
Οι σκιάσεις δηλαδή που κάνουν τα κτίρια.
Ναι, οι σκιές που κάνουν τα κτίρια. Αυτά συνήθως μένουν, γιατί τα κτίρια δεν μεταγίνονται. Οπότε αυτά τα obstacles μένουν και δημιουργούν correlations μέσα στο signal. Δηλαδή, αν κοιτάξεις το signal τώρα και μετά από μια ώρα, το effect of the building stays there. Sure. Ευχαριστώ. Okay. Οπότε οι σκιάσεις είναι αυτό που θα δημιουργήσει τα correlations στο signal, and we're going to explore these correlations to predict the channel in time and space.
Και το L είναι μήκος κύματος.
Το L είναι exponent that says how fast the signal attenuates with distance. For example, in open space is greater than 2. Outdoors.
It depends on the air and the quality of
it depends on the air, yes. If it's humid,
yes.
It attenuates faster.
If it's polluted air,
yes, exactly.
If it's rain.
Exactly. So if you look in the literature, there are values for this exponent. It's a well-studied exponent. This last term represents fast fading. Fast fading. So this is the result of small obstacles in the path of the signal. So if you have every obstacle that is of the order of the signal wavelength will create an effect, will have an effect represented by this term. Now, for example, 2.4 gigahertz, your Wi-Fi signal has a signal wavelength of the order of centimeters. So every object of the order of centimeter is represented by this term, will reflect the signal. And this changes very fast. So if you try to, if you transmit, let's say in here, a signal between now and in like a few minutes, the effect of this term will be different. Right? So it's fast fading.
So we can say shadowing is independent of time. Sort of.
It's not independent, but it's...
the statistics are in
the statistics are independent of time for some time period. After some time, they change the statistics. So in this work, we will assume a time frame over which the shadowing model parameters stay the same. So instead of working with this little f, same model is for the G. F is the channel from the source to the relays, G is the channel from the relays to the destination. Instead of working with that multiplicative channel model, we prefer to work with the log magnitude of the channel model. And when you take log of a product, you end up with the sum of the logs. So we'll denote that log channel as capital F, log magnitude of the channel as capital F. It has three additive components. Now this is the path loss, this is the shadowing, and this is the small scale fading. And if you want to go back from the capital F to the magnitude of little f, this is the expression. Now we'll statistically model each log component, log channel component. So this is a small scale fading component. We'll assume it's IID Gaussian. IID means independent, identically distributed. So we model it as a random process in time and in space. I represents position, T represents time. So if you look at these two components at different times and different locations, they're independent. But if you look at it as a random process, it's Gaussian with zero mean and this variance. If you look at the shadowing component, it's also Gaussian. The instantaneous statistics are Gaussian with zero mean and this variance. However, if you look at these components at different locations and different times, there is correlation. And the correlation looks like this. So if you think of it as a function of locations and times, the correlation based on this expression decreases in exponential fashion as the distance between the 2 points increases, and also in exponential fashion as the time between the 2 points increases. And the beta is the correlation distance, says how fast the correlation decreases between 2 time space points. And gamma is the correlation time, which shows how fast the correlation decreases between time instances k and l. So obviously, if you look at these components well separated in space, there will be very little correlation. So the correlation is contained within a small area, and the area is characterized by this beta parameter. Now, if we put all the channels corresponding to all locations in this vector, and this is for the source channels, we do the same for the destination channels. We can represent all the channels in the network in this vector form. And if we consider times between, like a time-slotted system, with slots 1 up to nt, we can put all f and g together and create a really long vector. So this really long vector contains the channels in the entire network, the f and g channels, at different instances from 1 up to nt. And we can show that this is Gaussian with some mean and some covariance matrix that depend on the assumptions, the parameters that we have chosen before. Yes?
The size of f, vector f, is as many as drones. So
No.
if I have f capital F is
No,
vector.
not drones. We fit a grid basically in space and time. So the size is how many grid points you have in time, in space, in all possible positions.
I'm talking about f, the f vector, right?
Yes. So these are all possible positions that you have.
All possible.
Right? The drones can go.
Because it says r to the r. It says r to the r down there.
Yeah, and
Below.
R is the number of grid points that we have.
Ah.
R is the number of
But below it says r to the r, right?
where?
Above. Here. What is r?
It's wrong. It should be the grid point.
It's
the
grid
number
point.
of grid points.
Oh,
Yes.
okay.
Thank you. It's wrong.
It's not number of drones. It's number
No.
of grid.
Yeah.
For all grid, which can be met too many. Right?
Yes. So it's up to you to fit the grid, and this is where the drones can be located.
Okay.
Okay, and we can show that this matrix is also positive semi-definite, which is good for the analysis later on. So let's look at the relay beamforming problem. So suppose that the source transmits a signal S of t. The signal goes through these channels, so it's multiplied by the channel. So for easier notation, we denote as Fi the flat fading channel between the source and the ith relay. So after going through these F channels, the ith relay receives this signal, the signal of the source weighted by Fi. So the relay weights the signal by this weight, Wi, the weight is to be designed optimally, and it's transmitted. So it goes through the G channels. So the weighted signal, which is represented by this product, goes through the GI channel. So it's received by the destination as in this form. And because the destination receives the contribution of NR relays, it's received the summation of these terms. However, the relays also forward noise, like measurement noise. So the measurement noise, which is denoted by this Ni, is also weighted and goes through the G channels and is received by the destination. Plus, the destination receives some measurement noise. So this represents interference and noise, and this term represents the signal that the destination is interested in. So this is the signal the destination is interested in, but it receives basically this function of the signal. And the question is, what is the optimal weights that the relays should use in order to maximize the signal to interference ratio at the destination? So if you formulate the signal to interference ratio, so this is the power of the signal component, this is the power of the interference, this is what you want to maximize with respect to the weights W. And of course you have some constraints. You are interested in power. The relays cannot transmit as high power as possible. There is usually a power budget. So the total power of the relay should be constrained by this PC. So this is a problem that one wants to solve in a typical beamforming problem. And this has been solved in this paper in closed form. They have shown that this is a generalized eigenvalue decomposition problem. And these are the optimal weights, and the maximum objective function is the maximum eigenvalue of the eigenvalue problem. So the interesting thing is that the weights at the mth relay are functions of the G and H channels that this relay sees.
Would it be GNF?
Yes, yes. I didn't have time to change it. He picked the same problem yesterday. Right. So this should have been F. And also there's this constant here that you want to ensure that you meet the power constraint. And this is the corresponding maximum SINR. You can show that the maximum eigenvalue is basically this summation of NR terms. NR is the number of relays. And each term in the summation contains the F and the G channels, magnitude square of the channels of that relay. So the interesting thing is the channels depend on the position. So we write this term as V1, that is a function of the position of the relays. PIs are the positions of the relays. So this says that this is the maximum possible SINR with respect to the weights. So we optimize the weights and we achieve this maximum SINR. And here we see that the maximum SINR depends on the position, which means that if the relays are positioned correctly, this maximum would be further optimized. So this is the problem that we're going to address. We're going to use the optimum weights to get this maximum, and on top of that, we'll use the locations of the relays to further maximize this SINR. So the natural question is, suppose that we have a time-slotted system. So the relays move at some point at t-1 slot. The oracle so the beamform, and then at time t-1, the oracle reveals to them what is the optimum position where they need to go to in order to beamform and achieve the maximum possible SINR. But in reality, there is no oracle to do that. So somehow, this optimum P of t needs to be estimated based on what we already know, what the relays already know. And in order to estimate this optimum position, the relays will use channel state information that they have seen up to that point. So once they go to certain positions, they can exchange messages and estimate the channels between themselves, their fellow relays, and the source and the destination, right? And they're going to use this information to find the channel at the position they have not moved to.
Κανονίζουν δηλαδή από μόνοι τους, ανταλλάσσουν τους μηνύματα σε ποιο slot θα ξεκινήσουν να κάνουν το relay.
Σε ποιο σημείο θα πάνε μετά.
Ναι.
Σε ποιο position στο χώρο.
Στο χώρο. Με βάση τι. Με βάση τι. Με βάση τη μεγιστοποίηση αυτού του προβλήματος που μας παρουσιάζατε.
Θα το εξηγήσω τώρα. Δεν έχω εξηγήσει.
Επειδή αναφέρεται αυτή τη στιγμή slot γι' αυτό.
So we are slotting time. So at each time instant, the slot is time duration. So I will explain this. So we slot time, and let's say in the beginning of the slot, the source transmits a frame containing data and pilots. The relays hear it. They use the pilots to estimate the channels between the source and the relays. And the destination does the same, sends a pilot, so they can use the channel between the positions and the destination. And they flood the network with this information, so everybody knows all the channels for that particular location. They beamform. They know the channels, they know what's the best way to beamform, using the expression for the weights that I have shown here. So before the end of the slot, they need to move to a next position, right? What is that next optimal position? This is what I will explain to you next. They need to estimate the next possible position. So at the beginning of the next slot, they are optimally positioned in order to beamform and achieve the best possible SNR. So it's like a two-step process. They beamform and then they move. They beamform and then they move. And by doing that, they optimize the SNR. So it's a two-step process.
Να πούμε λίγο τι είναι τα pilots.
So the pilots are the way we estimate the channel is we transmit something that we know. In addition to the useful information, we transmit something that the destination knows. So if it knows what it's supposed to get, it compares it to what it receives, and this allows the destination to estimate the channel, right? So it's very simple. If the signal is multiplied by the channel, the destination receives the source signal times the channel. If it knows what the source signal is, it can divide and find the channel, right? And assuming that the channel does not change in the next few seconds, it can use that channel to decode the information that does not know what it is, right? So the pilots are typically used in communications in order for the destination to estimate the channels. It represents overhead, but it's necessary because how else are you going to find out the effect of the channel? There are also more complicated ways to find the channel, but this is the most typical way to estimate the effect of the channel.
Μία ερώτηση ακόμα. Όταν λέμε ότι κάνουμε adjust το weight, αυτό πρακτικά τι σημαίνει για τα relays, ότι θα αυξήσουν ή θα μειώσουν το signal power, θα αλλάξουν τη θέση τους?
It's a very good position. So, very good question. So, adjusting the weights are complex numbers. So, effectively, they change the power of the signal, and they also shift the signal back and forth. So, imagine as the sine wave propagates, depending on the distance, it will be received at some phase difference at the destination, right? If the relay knows what is that phase this difference, it can take care of that by delaying the signal a little bit. And you can think of each relay delaying the signal by just a little bit so that all arrive at the destination at the maximum point. You can think of this as simple as that.
Έτσι ώστε να συγχρονίζονται οι κορυφές των βουνών.
Είναι κάτι σαν να κάνουμε time scheduling, ας πούμε.
Exactly, yes. So this complex number introduces a phase to the signal. The phase means that it delays it effectively, right? By as much as it needs to in order for all the signals to be received at their maximum point. Okay? Of course, this assumes that you know the channel, right? You know how much the signal will be delayed when it goes through the channel, so that you sort of proactively counteract that, right? You delay it by whatever is needed, so that as it goes through the channel, this delay effect is counteracted. Other questions? Okay, you're asking good, all these are very good questions. Please feel free to ask questions. Okay, so after they estimated the channel, they can beamform. And then they need to decide, at the end of the slot, they need to decide where to go to, based on the channel knowledge that they have gained up to that point. So in the next slide, I will tell you, assuming that they know where to move to, how they're going to move to. Because there is a control problem that they need to solve. Like if U is a motion controller, the motion controller is the derivative of the position. And if this is the position at time t, it can be expressed as the position at t minus 1 plus the integral of the motion controller over the duration of the slot. So if we want to move the relays over a straight line, if this is the optimum next slot position, and this is the position at time t minus 1, then the difference over the duration of the slot is the optimum controller. So if I give you this optimum position, then you know what is the controller that will send the relays there, right? So this is a vector that has all possible positions. So if I give you what is the optimal vector, you can build a robot that will send that will go to this optimal position using this controller, if you have taken controls class. So I will explain to you now how we find that optimal position. So we'll find that optimal next slot position by solving a stochastic optimization problem. So remember that VT, that is the optimum SINR, obtained by using the optimal beamforming weights. We're going to maximize the average SINR with respect to the optimum next slot position. So we will maximize the expected SINR with respect to the next slot position, subject to some constraints. What are these constraints? We want to make sure that we are moving in small steps, staying within the neighborhood of the previous optimal position. Because remember, we're going to exploit statistics of the channel, and the statistics die out with time, right? So we don't want to move too far. They die out with time and space. So we don't want to move too far away from the previous optimum position because there are no statistics that can be used to take us there. So this constraint says that the movement will be within the neighborhood of the previous optimum position. This says that the optimum position will be function of the channels that we have seen up to that point. We're using causal channel state information. That's what this says. So initially the relays are positioned in some arbitrary positions, and we want to find the next slot position by maximizing this. This is a very difficult problem. This is a stochastic optimization problem because this is random. So we're maximizing this statistic with respect to a random variable. So it's difficult, but we can look at a simpler problem that is a conditional expectation problem that we want to maximize. We want to maximize the V function condition on knowing all the channels up to t minus 1. So because P of t is function of these channels, when you condition, you assume that these are already known, they're fixed. So this is fixed also. So this is an easier problem to maximize, and actually there is a theory, the fundamental lemma of stochastic control, that says, this is the simpler problem that we can maximize, and that lemma says that the expected value of this problem, of this maximum, is equal to the maximum of the original problem that we wanted to solve. And also says that if I find the P that maximizes this problem, the same P will maximize this problem. We can continue working with this smaller problem, the conditional expectation problem. And if you recall the expected value of the SINR can be written as a summation of terms, each term pertaining to a specific relay. So if I want to maximize the expected value of that, I can bring the expectation inside the summation. And if I want to maximize the summation of terms, this is equivalent to maximizing each term in the summation. And remember, each term pertains to a particular relay. So here we have a problem that each relay can solve individually, finding the next best position. And by solving this individually, effectively, the entire SINR is maximized. So this is a nice distributed problem. It will take several steps to solve this problem. We can see that inside the expectation we have a function of the magnitude square of the F and G relays. And if we want to compute the expected value of that, we're going to have to use statistics of the magnitude of F and the magnitude of G. And the assumptions that we made allow us to compute these statistics in closed form. Basically, you can show that this function depends on expectations of this form, magnitude of F to the n, magnitude of G to the n. And if you bring this, if you bring the capital F back, then this is basically the joint characteristic function of jointly Gaussian random variables, and there are closed forms for this expectation, as you see here. So maybe I shouldn't bother with the details. So we were also able to show, so we can solve this problem. We were able to show that if some relays stop moving because maybe they experience failure, let's say these are robots that stop moving but they still retransmit, then we have shown that the expected SINR will not decrease, will stay at the value that it has been achieved up to that point. And also it shows that as time increases, the expected SNR does not decrease. It stays the same or increases.
This only applies to vehicles, cannot apply to drones.
Yeah, the SNR, the expected.
No, I mean failure and still complete, still transmitting, it only happens to...
Yeah, if the drone falls, maybe it can still transmit,
oh,
it will
okay,
be far away, right?
Right.
Unless it's breaks
Yeah,
completely.
okay. But, I mean, it doesn't have to be drones, it can be vehicles, right?
Yes, it can be vehicles.
Maybe boats.
Boats, cars.
Right?
Yes. Cars on the highway
Cars
are very
on the
well
highway.
beamformed.
Drones is just an example.
Yeah,
No one's-
right.
yeah.
You like to call them drones, but
Yeah.
they... So back to this example, I'm going to show you some simulation results. So we consider a scenario like a 30 meter by 30 meter space, and we have a number of drones in here that are moving in this 6 by 30 meters area. And in particular, we consider these parameters to model the channel, and these parameters for the power to be used. And the relays, because it's a very difficult problem, there's a lot of parameters, we fit a grid on space, and we say that the relays will only move in forward, backward, left, right, and diagonally by one grid point only. So, or stay in the same position. So there are 9 positions. We also need to implement collision and out of bounds control, because what if the relays choose the same position to move to, there is going to be a collision, or they can fall out of bounds. So we also did that. And this is for 8 relays. This is the expected SNR, so we did a lot of trials. For each trial, we found the SNR, and after 4,000 trials, I'm showing here the expected SNR. So this is expected SNR versus time slots. And this is if an oracle told these relays where to go to, if they're optimal position. Then you would achieve SNR of over 10 dB. This is a line corresponding to a scenario where the relays move randomly. They don't care about optimizing their position, they just move wherever. So you can see that you don't have any SNR gain. And these are the two lines corresponding to two different approximations of the SNR for the proposed method. And you can see that you achieve like 7 dB after 40 time slots, about 7 dB SNR gain. And this is, again, expected SNR versus time slots when some of the relays experience failure, 0, 1, 3, or 5 failures. So we showed that on the average, and asymptotically with the correlation of the channel, the SNR will not change if some relays experience failure. And here we sort of see that the failure happens at this slot, at slot 12. And this is when there is no failure, this is 1 failure, 3, and 5. You can see that there is some small change, but not significant, if you look at this scale here. But I'm going to show you a figure next where we use stronger channel correlations, where you can see that this discrepancy is even smaller. And this is the agnostic scenario where the relays move randomly, and you can see that there's no SNR gain. This is a scenario where the relays fail earlier. They fail at slot 4, whatever that is. And at that point, the SNR does not decrease. It stays, it either increases or stays the same with the SNR achieved up to that point. So when you have 5 failures, it stays the same. When you have fewer failures, it keeps increasing. So this is a scenario where you have stronger channel correlations. Before it was 5, the gamma here is 15, which means that the channel is strongly correlated. You have stronger shadowing, bigger buildings in the path, where failure doesn't matter significantly. You can sustain the expected SNR even after failure. So some other problems that one can consider with this technique, this idea, that has to do with physical air security. Now, what is physical air security? Typically, to maintain secrecy in communications, like to prevent an eavesdropper from intercepting information, is secret keys. Like you have to use secret keys in the transmission, and only if the eavesdropper has the key can unlock the information. However, these days, with a lot of computational power, secret keys can be easily broken. And further, it's difficult to distribute secret keys over a wireless network. Somebody can intercept that information also. Right? So there is a lot of work going on in maintaining security of communications without secret keys, by manipulating the wireless communication channel. So one way that this can be done is the following. You have a source that wants to communicate with a destination. And you have a bunch of eavesdroppers here that are interested in intercepting this communication. Right? So how can I prevent them? One simple way is you enlist the help of some relays that are close by, and they could be trusted. So these relays can they can forward the signal in a form that focuses the signal power to the destination and avoids the eavesdropper. Can formulate a beam, design the beam. Yes.
Δεν είναι λίγο ρίσκι αυτό όμως, γιατί αν κάποιος θα μπορούσε να κάνει exploit τα relays, θα μπορούσε να κάνει ούτως ή άλλως man in the middle, λέγοντας τα relays να πηγαίνουν και το traffic όλο σε αυτούς και να το κάνουν αυτή ανακατεύθυνση, να κάνουν αυτή τα relay.
Yes, so that's why I said that the relays are the nodes that are trusted, right? So if the nodes are trusted, then they can form a beam to send the signal to that destination. This assumes that you know where the eavesdropper is, because if you want to exclude the eavesdropper, you have to know where it is to avoid the eavesdropper. However, there are other techniques that do not need to know where the eavesdropper is. For example, these guys can send the signal to the destination here and create noise everywhere else. This is called creating artificial noise, jamming basically the eavesdropper. And they can formulate a beam so that they jam the entire space except the destination. They can form such a beam that jams the entire space except the destination. And of course, you can do that more effectively if you are allowed to move these relays, right? Or if instead of moving them, if you can select the relays. As you said, some relays are not good, maybe you cannot trust them. You can, actually there are called reputation schemes, where you monitor the relays and you can tell who is friendly and who is enemy. With machine learning now this is relatively easy to attach a reputation score to the nodes of a network, and you know who you can trust and you cannot trust. And of course this changes with time. So you can select the good relays to help you with this problem. Another potential application would be to construct a smart, physically reconfigurable antenna. So what this means is that you're here, for example, and you want to make a phone call, but you don't have good reception. You could have a grid of antennas somewhere on the wall of the building, and these antennas could move in specific directions, up or down, and they can move real time in a way, and they can be optimally positioned to strengthen your signal so that you have better reception in this space. You can think of this as one application. Okay, so this concludes my presentation. We consider the mobile beamforming problem formulated as a two-stage stochastic optimization problem. We use only causal channel state information, and the problem was a distributed problem. In other words, each relay could solve it independent of the relays and still optimize the overall problem. So I would like to thank you very much for your attention.
Ευχαριστούμε πάρα πολύ. Υπάρχουν ερωτήσεις?